Hello and welcome to Dunjun. I'm Bill and this is a series where we're documenting and demonstrating the process of making a game from scratch. Today is day 20 and in the previous 3 days I did 3 Blackboard videos. First one explaining the introduction to complex numbers and how they're used for 2-dimensional rotations. In the second one I did introduction to Quaternions and how we use them as rotations for 3 dimensions, and in the third one I explain Quaternions and the interpolation between them and how we interpolate between different angles and how to do it using slurp and S-quad, so spherical linear interpolation and spherical quadrangle interpolation. So let's go on to that. If you want to follow along, just please go on to the GitHub page and make sure you get the latest commit for this video. So we are on day 20, so go to the day 19th comment, we'll be fine, and follow along there. The other thing I've changed since the previous day we did any code is all I have done is I've added the depth buffer bit into here, and the reason is because we're working 3D now, and the depth buffer bit will make sure everything is doing it correctly. Okay, and this won't do any bad clipping. So let's go and start implementing our own Quaternion class. Let's go into math, into functions, and not source, let's go into the include bit here, and let's add our own new item. Let's call this Quaternion head++. For the define guard, so this is if not define Dunjun math Quaternion head++ define namespace Dunjun like so. That should be all we need to do. So the Quaternion, we need to what I'm going to do is represent the Quaternion as a vector and a scalar. That's what we've been doing before, so please watch the previous videos if you've not watched them. So what I need to do is include Dunjun math. I figured out how to do the autocomplete now for all this stuff. It just wasn't working as bulk with Visual Studio. What I'm also going to do is also make sure I include math and the angle, and also include Dunjun math and the constants. Yeah, that's what I'm going to do. I think we'll have to include some more. So we also have to, or will include, is the matrix 4, because we'll need to convert from Quaternions to matrices eventually. I didn't realise it adds the thing on automatically for me. So let's create our Quaternion. It's going to be a struct, like what we did with the other stuff. So Quaternion, it's a struct. So let's just format this already. Done. Perfect. So, sadly, in this version of Visual Studio at the moment, not until 2015 will this be finished. In 2013 we haven't got unrestricted unions. So what we have to do is represent everything else. So what we're going to have is a vector 3, yeah, and this is going to represent our the x, y, z, so the vector part, and we're going to call it x, y, and z, yeah? And then the scalar part will just be a float 32 and represented by w. Now the reason why I'm doing x, y, z and w rather than v and s, and it may seem a bit confusing, but the reason why is in GLS, comma, a vector 4 is actually an x, y, z and w, and when we're doing the calculations on the other side, on the shader side, this is what we're going to use. We're going to use Quaternions rather than matrices. We're going to have to convert the x, y and z and just use that and then get the w component on its own. So we're using it backwards, but only because of the shader more than anything else. It doesn't make any more difference, really. So let's start with that. So let's create some constructors, Quaternion, and the default constructor will have the vector, the x, y, z thing will be 0, 0, 0, but W will be 1. Now, as we learned in the previous episode, that means we've got no rotation axis, and we've got no rotation, because cosine theta is 0, and there's no rotation axis. But that's perfectly fine. This means it's just a plain old scalar, and that should make any difference. So let's just quit this to make sure, is it actually working properly? It's not doing anything. Does this still compile? Just make sure it compiles. Yeah, it still compiles. Everything's still working kind of correctly. Just double checking. So now let's go to a quaternion. Oops, and do the copy constructors. And just do quaternion q equals default. I'm too lazy to do it. The next thing we can do with quaternions is we need to do an explicit cast of it. So quaternion, and then we're going to have a vector 3 const vector 3, oops, v, and a const, not const, just needs to be float for the scalar. That's what we're going to do. X, Y, Z equals v, and w equals s. Again, you may be asking why I don't just v and s like I did in the other thing. Again, it's just for that. And when until we get unrestricted unions in Visual Studio 2015, that's when I upgrade to it straight away, I won't use it. I know there's a preview edition at the moment this time is being recorded, but I don't want to use that because it's still not what I want to use. So that's how we do quaternions. And then the last thing, we could explicit as each of the components, but I won't do for numerous reasons. So next, we're going to create another thing. So other nice little functions. What else is there? Try to think. Oh, I know what I think. Yeah, we're going to just create some functions first. So we need to get the dot product. So let's say dot with another quaternion. Yeah, the other quaternion. Let's say this is q, and this gets as const because it's not going to change anything. This is going to be the dot product, and as we did before, the dot product is equal to return x, y, z. Yeah. Just dot this product first. So dot that times by q x, y, z. So the other one, x, y, z. I'll write other. Just be a bit more explicit. Other plus the w in this one times other dot w, and that's the dot product, yeah. And that gives the dot product one of the simple multiplication things. The other thing we could do is get the length squared, so it's magnitude squared. Yeah. So that's just doing the dot product with itself. So return dot this. Yeah. And then, as we did before, I'm going to is CMath included? It should do in the others. We're going to include the actual length of it, and this should just return the square root of the length squared. There's not the autocomplete is not working for this at all. It should be standard square root. So what I'm going to do is actually just close this. Oops. And close that for now, I don't need that. And restart Visual Studio. Please, restart. Yeah, it's working now. Too many arguments for dot. Yeah, that's why. It's using the wrong dot. It's a bit ambiguous, isn't it? Or is it? No, it's not. This should be a vector dot, so actually, maybe I have to write it like that. Vector 3 has no member dot. So let's see if that compiles. It should compile. Yeah, it compiles fine. Actually, one thing I haven't done yet is actually included this into the math header. So I'm going to include that here. Include Dunjun math quaternion. It should maybe, yeah. Here we go. It's a bit ambiguous. It doesn't know. This is not correct. Well, it's not this dot. It's actually the other one. It should be the vector 3 dot product. But it's thinking here, so it's not. So what I might have to do is do it outside the actual function. Make this inline. So let's do the dot product outside. Yeah, that's not a bad idea. Let's do A and B. Yeah, I'm doing this as I'm just working this out as I go along. A and B. A dot and B dot. That works perfectly fine. And then this one, what we're going to do is have to do everything ourselves. So we're going to do the dot product of x, y, z, plus the w times w. This should now compile perfectly fine. Yeah, there's no problems. Perfect. So we've got length squared and the dot product and the dot there, yeah. Next we need to get the normalized version, so how did we write it in the vectors? Oops. Math. Vector 3, did we just say normalize? Yeah, normalize. Is an outside vector, yeah. So to get normalize is Quaternion normalize another Quaternion. Yep. What we'll return is the Quaternion, yeah, multiplied 1.0f divided by the Quaternion's length. Now this means we haven't done any multiplication yet. We haven't done any of its operators. So the first thing we need to do before any of the operators is, so I'm going to do these actually after these functions, that was the thing I forgot. So we need to do the Quaternion, we need to do the negation operator, so make everything negative. So what we're going to do is we're going to get a temporary variable. So c.w equals negative w, c.xyz equals negative xyz, and then return c. Yeah. Okay, that seems good enough. I've done this explicit, but again, I don't have to do it explicitly. I might just comment that out just for now. Oops. Comment. I might get rid of it later. I haven't decided yet. So next we do addition. So Quaternion operator addition with another one. Quaternion. Let's just use the B notation. Yeah, it might be easier. So let's do this Quaternion C and stuff. So C equals B dot W plus B dot XYZ, and then return that. That's good. The negation, negative, subtraction, whatever. Move that and return with that. Now we've got multiplication. Now I'm going to just write a note in here. When we multiplied two Quaternions, it was a little bit confusing. So, operator with another Quaternion, B. And what I'm going to do is Quaternion A equals this. And actually what I need to do is actually that's a const reference as well. Const reference, yeah. And I'm also going to have a little end one, so Quaternion C, yeah. So when you multiply two Quaternions together, let's say Q in this case is scalar. I'm going to do it the other way around. This takes vector and a scalar. So where V is the vector 3 and the S is the scalar, or in this case it's a float 32. The multiplication, so between V1, S1, yeah, and V2, S2, it was equal to, let's do the vector part first. That was S1, V2 plus V2, no, S2, V1 plus V1 crossed with V2. Then the scalar part was S1, S2 minus v1 dot v2. I won't put a dot, yeah, I'll put a dot space between that. Like so. So where dot implies dot, I'll just do that, yeah. Dot product, and cross is a cross product. Yeah. So what I need to do now is, I know what the long version is, I've got it written down here. So I shouldn't do it the wrong way around. Let's do x first. So x equals aw times b dot x plus a dot x. Oops, we haven't got the x components, have we? So actually we could write it like that, or would it be more efficient to write it the other way? Yeah, one other operator I might actually do is Quaternion. Not Quaternion, it'll be float32, won't it? Operator. That. Index const return. And what we're going to do is actually cast this as a float32 pointer. This is going to be cast as a pointer. Does that work? No. Does that? Why does it type invalid conversion? So what we're going to do is may work, might not work. Oh, why doesn't that work? No, it doesn't work. So it should have worked, but okay, let's just do it the long way. If index is less than 3, yeah, return xyz index, else just return w. I'm just going to say that for now. I'm going to write to do fix me to do me test for out of bounds. Like so. Okay, that seems good. So what I'm going to do here is, I could do it write it like that, but it's not very efficient. But if we did write it like that, all I have to do is c dot the vector part x, y, z. Actually, all that equals to is the vector part is a dot w times what is it, b dot x, y, z plus b dot w times a dot x, y, z plus the cross product between them. So the cross product of a and b. That should work. Oops, no, a. Like so, that's okay. And CW would equal AW times BW minus the dot product between AX and B dot AX, Y. This is not very efficient, I know. Technically the more efficient way is what I've got written down here, but it doesn't work because we've got the vector components and stuff. So I might just have to rewrite that. Yeah, so I'll need to rewrite this. New function to do make more, make efficient. Yeah, not using cross product. Yeah, because that's a bit costly as well, actually, thinking about it. Next we've got to do a quaternion with a scalar. So I'm going to do this C again. And what I'm going to do here is that when you multiply by a scalar, what do you do? So this is going to be C equals this for now. And then C dot xyz times equals S W return C. Should be all we need. And then division by a scalar as well. Just check in. Like that. Next thing to test is if they equal. That's another thing to test. Just say bool in this case. We don't need to worry about bool later. We'll, when we get down to it, we will. When we do optimizations, we'll do it later. So const quaternion. Oops. Quaternion q const. Is q? Let's just say other or b. We've been using b for everything, haven't we? Yeah. So for u size I is less than 0, I is less than 4, I plus plus. If what's a better way of putting this? If operator I doesn't equal bi, return false, else we're going to return true. Operator equals operator I, like that. Yeah, that's the way of doing it, yeah. That's the way you write it, yeah, I'm just thinking about it. And then the not equals bool of operator not equals, it's just just screw that. Return the opposite of that operator. So that's all the things we need to do. And the other thing we need to do is swap the scale a bit around. Quaternion operator here. We need to do float 32 and the quaternion. Q for this case, yeah. And return Q times S, because it doesn't really matter which order you do the quaternion. The dot product between two quaternions is that. And now the cross product between two quaternion is a little confusing, so I need to do that. Quaternion cross product. So you get a rotation that's perpendicular to itself. What else? We need the conjugates, don't we? Need all that lot. So inline quaternion conjugate then what we're going to do is quaternion C equals Q. No, actually no, what is C equals Q on X, Y, Z, Q, Z, W, and that part needs to be put negative. And then we return C, that's the conjugate. Inverse is what I need to do next as well. So we're going to do get the conjugate, so that equals conjugate of Q divided by its length squared. So all we do is Q dot length, or let's just say dot 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 Q Q, like so. What else? We've got rotate around an axis, convert to a matrix, and all the other stuff. Oh, there's a lot of them, thinking about it. One thing I'm going to try to keep this episode short is the other one. I'm going to do, oops, O stream. we're just going to print it out. So what I'm going to do is standard O stream operator. So we can just print out this Quaternion. So Quaternion. And then what I'm going to do is for use size I equals 0, I is less than 4, I plus plus. What I'm going to do is go through every single one, print it. If I is less than 3, what I'm going to do is OS do that, I'm going to print thing and else at the end. I'm going to put a bracket around the end, return OS. So all I'm doing is printing Quaternion, printing every single element, and after, except for the last one, we put a comma and a space. That's all we're doing. So let's just test that still works, it compiles. Okay, that works. So let's do some tests in the main. We need to test if this actually works, because for all I know, it could be completely wrong. So let's do the tests here, this will be good. So let's, using namespace Dunjun, let's get Quaternion A, and this is going to be defined as vector. Let's just keep it as A for now, and a Quaternion B. Let's just to see if the scalar bits work. So we got 0, 0, 0, and the scalar bit's going to be 2. This should still work. And then we've got another bit version here. So I'm just going to put some random numbers in here. Actually, no, let's do what? Do 1, 4, negative 4, negative 4. Well, no, it was the negatives there, weren't they, last time? Yeah. We don't need to put brackets around that. The scalars. Like so. Let's see if that compiles. Yep. So what we need to do some tests. We're going to do standard cout A. And do B. They should both render out correctly, so you got 0, 2, and there, yeah, they're perfect, lovely. The next thing we're going to do is test out their inverse. So Quaternion, we're going to do the dot product between the stuff, so dot B and B. What we should get is, I think, 49, was it? Yeah, we get 49, that works, it does work. And so we know the dot products work perfectly. The next thing we're going to do A times B. That should just multiply every element by 2, and it doesn't work. So it must return a value. We've got an error. Here we go, we didn't return C, did we? Return C. This is why we need to check stuff. And yeah, it's multiplied everything by 2. Let's go back to what our example was before, where we had only 2i, so it was in that bit and that, and we'll get it and then, oh no, actually, yeah, 2i was a position, and then its rotation was whatever. I don't know, I'm just making this up. Like so. But, so that's our position, B times that, times by its, is it conjugate? Yeah, B. Should be completely real. Yeah, pure, it works perfectly fine. So that seems to work. Okay. One thing I'm going to do now is the operations between a Quaternion and a vector 3, so transforming a point. Now I'm just going to make a little helper function, yeah? So do it here. Vector 3, we're going to transfer operator, const Quaternion q, const vector 3, oops, I can't find it on this keyboard, never can, there. So what we're going to do is actually we're going to return q times Quaternion of v0 times the conjugate of q. That's what we're going to return, yeah? but this is more expensive. There is a little trick to this one. All we're going to do is say vector 3t actually equals the cross product between q, x, y and z and v. This is much cheaper to do. Then all we do is v plus qw times by t, where this is the q times t plus the cross product of q dot xyz t. And this is a much quicker way. Even though he's in cross products, we could write the out much easily, but it actually does it much more quicker than doing that version. Because what you're doing there is quite a lot of more. You're doing 3 different things in there. So when you do multiplication here, you do a cross product. So what you're doing here is doing 3 cross products, but here we're only doing 2. So it's still cheaper to do it that way. So now we can rotate a point, and that should work. I know it should work, so I'm not going to test that. Anything else that we need to do? That should be okay. I think we could set default values for that anyway, can't we? I think that can be set as the default values. Oops, vector 3. Oops, I need that. MC plus 11. That should work, I know, but eh. So that's our Quaternion. How much time have we got left? 10 minutes. Let's see if we can implement a few functions here, so we can get the angle and stuff, like those functions. Yeah. So these are going to be the angle classes. What we need to do is implement... actually, let's keep the last thing here and just do it here. So now we need to get the angle from the Quaternion. To do that, all we do is I'm going to say it's a radian angle, const Quaternion q, and all we have to do is return 2 times the arc cosine of qw, so the scalar part. That's all we need to do, and that gives us the angle. Now the axis is a bit different. Inline vector 3 axis const Quaternion q. To get the axis, how we did before was a bit different, but we're going to test something first. So we're going to have is the temp variable here, temp 1. And what we'll do is 1.0 minus qw times qw. What this gives us here is sine squared theta. This is actually 1 minus cosine theta, let's say theta over 2, and that's squared, isn't it? So let's just multiply that again. Which is the same as sine. Over 2. That's the same thing, yeah? So we're next, if that angle, if that bit there is less than 0, we're just going to assume it's the up vector. We're just going to say what it is, because it's failed. So it's less than or equal to 0. What we're going to say is return just a vector 3 of the up vector. Just assume it's the up vector for now. So that's okay, that's all working. We're now going to get the length of that new, we're going to get the inverse sine of that. So inverse temp 2, this will be 1.0f divided by standard square root of temp 1. Actually, what I'm going to do is call that S2. That's S2. And this one is going to be inverse S2, just to make it a bit easier to read. And then what we'll return is return a vector 3 of, we don't need to do that, we can just say q, x, y, x, q, x, y, z, times by that inverse S2. Yeah, lovely done. That gives us the axis. Now what if we wanted to work the other way around? Yeah? Let's do it the opposite way around, so we get to the angle and axis and go to quaternion at the end. So if we do that, quaternion, angle, axis. So let's put a radian in, angle, and a vector. Oops. And this will be our axis. We need to make sure we normalise the axis first. We're not assuming that. So let's just make quaternion Q and then return Q. And then we're also going to make sure the axis is normalised before we even do anything. We're just going to do it. We're not going to assume. We could assume, but it would just be a bit daft. So we're going to say, we're going to call that A. Vector 3A. This is still going to be const though. Equals normalise the axis. And then we have const float 32. This is going to be the sine bit. So standard sine of 0.5f times by the angle. However, what we've got a problem here is we need to cast this all as a float for it to work, because that sine function doesn't work with radians yet. We will do our own. X, Y, Z will actually equal to A times by S. And then the W component is going to equal to the standard cosine bit of that. So that's our angle axis. So we get a quaternion from an axis. What else could we implement? Thinking about it. Okay, the other thing we could do is, I'm thinking, I didn't explain how to do this, but let's calculate the Euler angles first. So I'm going to create a struct of Euler angles and get the Euler angles from it. Euler angles. And the Euler angles we could have, they're all in radians. We could have, what would they be? That's a nice way of putting it. We could say pitch, yaw, and roll. They're the Euler angles, yeah? And what we need to do is we're going to convert them. So before we even do that, we're going to create some functions. Get the pitch, roll, and yaw. Okay, so in line of radian, roll. I'm just going to copy and paste the quaternion bit every time now. Much easier to write. And to get the quaternion roll, I'm just going to explain it to you what it is. It's going to be arctan 2 of 2 times by qx times qy plus qz times q thingy. Yeah, that's right, yeah. So it's qx times qy plus qz times qw, yeah. And then we have it's going to be qx, yeah, times qx plus qz, w times qw minus qy times qy minus qz times qz. So that gives us the roll from that. Pitch, and then we got yaw. I've done these in the wrong order actually, I'm doing, it doesn't matter. Pitch and yaw. Pitch is a bit different. What we have is y, z, zx and 0. then what we have here is it goes Z, X, and that should be Z takeaway actually. Takeaway Y. Oh no, Y should be 1. And Z should be a plus. They've just been swapped around, that's all we've done. And then the yaw is going to be a bit different. So what I should do is that should be a radian, it should be explicit cast. It won't work otherwise, will it? No. And then the yaw is a bit different, it's actually at the arc sign this time. So it's -2 times by X times by Z minus Q W times by QY. Yeah, I really want unrestricted unions. I'm thinking may not even keep them in the vector and other parts now and just give them X, Y and Z. I may change that eventually, but for now that should be fine. Let's see if that can... Oh god, is that working? 5 overloads? What do you mean 5 overloads? Oh. Yeah, that works. Whoops. Aha, there should be a radian. Yeah, that should be S2. Pile. Perfect. So let's test out our new things with some functions. So we'll go back to the Quaternions. Let's just initialize these and not even give them anything yet. What I'm going to say is A now gives us an angle axis. And we're going to rotate by, I'm using degrees. So it's 90 degrees, no, 45 degrees, yeah. And the axis we're going to use is the Z axis. Yeah, that's Z, vector 3. So that's our angle axis. This is going to be Q. I'm going to change this all to Q. And P for our point. So I'm going to get a vector 3 to be our point. Yeah? And that's going to be Q. And our point is going to represent a point in plane. So it's going to be 2, 0, 0. That was our example, I think, that we used. So if I print them, yeah, they should work, yeah. Oh, look, it's got a 0 component in there. That should be expected, though. Yeah, is that right? X, and then, yeah, that's perfect, yeah. Remember, it's backwards, X, Y, Z, W. So now, what we're going to do is do 2 tests. So we're going to standard Q times quaternion of P0 times by the conjugate of Q. This will represent a rotation. And we got it rotated, yeah, that's what we expect it to be. So we got rotated round the, this gives the new axis, so we just cover that bit, rotated it, the 2 point around the Y, Z axis, and we got 2 new bits there, yeah, got it into the X, that makes sense, yeah. We're going to test out the new way with Q, just has to be multiplied by P, it should get the exact same answer. This is the same examples I used in the Quaternions bits. Yep, we get exactly the same answer, so we know that this works. Actually, what I'm going to do is that. Do it as an X, Y, Z. Yeah, they both work perfect. So we know the other form works. Let's try a different axis, which is a bit off-centered. It should still rotate it correctly, yes. So our rotations work perfectly. The only things we haven't done yet in today's implementation, we're going to go into the Quaternion and give us some to-dos. I did the Euler angles, I didn't do the pitch, and I actually just Quaternions, Euler angles, return, what is it, pitch, Q, yaw of Q, and the roll. That was the order I did it in. Oops. And so what the thing was, Euler angles. Oops. That works perfectly fine. So what we need to do for tomorrow, later, so probably tomorrow, yes, to do is implement Quaternion to matrix 4. Matrix 4 to Quaternion, assume it's only a rotation matrix. What else do we need to implement? Yeah. Euler angles to Quaternion. We need to implement, I'm writing loads of different implements to do's here. We've got to implement lerp, slurp, and S quad. Maybe S quad, I don't know yet. And also maybe mix as well. It's not the same. But yeah, we've got mix. Mix is slightly different to slurp, but only slightly. It just tests for some things, that's all. Yeah. Just checking my notes, what else we have to do. Apart from changes to matrices. Oh, we haven't done our own rotation class as well. We've got to implement a rotate a Quaternion. So we could just multiply it. That's normally the way of doing it. But radian angle. But we're not going to do that. Yeah. Sorry, today's probably not been very good. But we need to implement that. Angle. Yeah, there we go. So in today's episode, we've implemented Quaternion. We've only got some of it down. We've got loads of to-dos left. Yeah, so maybe make that explicit rather than implicit. What I need to write down is note. Separate XYZ or swap yeah, I'm going to put a note there. I'm not sure if I want to do that. So what I'm going to do is implement a Quaternion, and it's represented as a vector and a scalar, but it's kind of the wrong way round, or S and V. I'm still not sure how to represent it. It's still a bit confusing. I'm not sure if that should be explicit or not. There's loads of stuff here I haven't decided upon yet. We need to test for out of bounds for these. That doesn't matter if that's constants, doesn't matter. Redundant negations. Other two, we need to make this more efficient so it doesn't use the cross product. We can just write out the elements itself because we know what it's going to be. It's a figured out product already. And it doesn't use the dot product. You don't need to do that. What else is there? We need to do the cross product of two Quaternions, so get Quaternion which is orthogonal to two Quaternions. May not seem very important, but yeah, why not? What else is another to do? Yeah, we need to implement Quaternions rotate a Quaternion by an angle. around an axis, given axis. We could just rotate 2 Quaternions together, but I'm not going to do that. It might be the reason why I'm going to do something else. Actually, you know what? I could do this now. I'm sorry. I'll do that. I'll do it later. I ran out of time already. Got to Quaternion. I'm going to do that to Matrix. And do all of them. So stay tuned for the next video where I'll implement all of them. So stay tuned to that, and goodbye.